This is geometry. We're proving triangles congruent, and then we're going to look at the corresponding parts that are congruent because of those triangles. So our first picture, we know from the given information, remember every time you do a proof you want to look for the plan, figure out how it can work before you start to fill it out. AB is congruent to DE. Angle ABC, look at the middle letter, that's where the vertex is at. That's the angle we're referring to, ABC. And angle DEC, they're supposed to be congruent. Well, that gives me a side, that gives me an angle in one triangle. I need something else. I don't know about a midpoint, but I do have vertical angles. So now I can prove the triangle is congruent using angle, angle, side. And if these two triangles are congruent, then I can say that their corresponding parts would be congruent. That DC would be congruent with AC. So that's my plan. I took my given information, I made the tick marks, I see how it can work. Now I'm going to try to come down and do the formal explanation. I have my two given information. I see that angle ACB and ECD, those are the vertical angles we talked about. If vertical angles then congruent angles. That gave me enough information to call the triangles congruent by by angle, angle, side, congruence. And we now know we have the additional parts. If you look here, the first and last letter correspond with the first and last letter. So DC is congruent to AC. Segment DC is congruent to segment AC. If two triangles are congruent, then corresponding parts are congruent. Now there is a fast little abbreviation for that, Cpctc. Corresponding parts of congruent triangles are congruent, Cpctc. That is a quick explanation of this if-then statement. So here we have BD congruent to CD. We have angle BDA congruent to angle CDA. And we're supposed to talk about how angle BAD, this one up here, is going to be congruent to angle CAD, that angle. I don't want to mark it now because that's not what I know. But that's what we're trying to do. So it looks like if I could just use these two triangles, so I have the B, the A, and the D with the C. We know those segments are the same. We know these angles are apparently congruent. By the reflexive property, I can show the triangle's congruent now by side, angle, side, and the corresponding parts are going to be congruent. So let's try to write that up. Step number one. I have segment BD congruent to segment CD. I also have angle BDA congruent to angle CDA. That was from my given information. I also noticed that the reflexive property, segment AD, was going to be congruent to segment AD. We have the letters going in the same order because we're going from the unmarked angle to the marked angle in both cases, A to D, A to D, so the shapes are not twisted. What's our reasoning for that? Reflexive POC. Whenever the triangles are sharing the exact same side, that's called the reflexive. There's one location that they both share. So now we know the triangles are congruent. So triangle BAD, bad triangle, with the CAD, the CAD triangle. They've got to be written in corresponding direction, where BD, first and last, goes with CD, first and last, AD, last two letters, with AD, last two letters. And those triangles are congruent because of side, angle, side congruence. Now what we're trying to prove is always our last statement. Angle BAD is congruent to angle CAD. That would be these two angles up here. Angle A of this triangle, which is the middle letter, is congruent to the angle A of that triangle, which is the middle letter. If two triangles are congruent, then corresponding parts are congruent. Okay, using the letter Cpctc could be an abbreviation for that. But remember, the if statement implies that we had to already say the two triangles were congruent. The then statement tells what we're talking about now, and these are corresponding parts. You just can't say then congruent. You have to say the corresponding parts. On the flip side, what we're trying to prove is that the diagonals of a rectangle, diagonals are the segments that go from vertex to vertex in a polygon that are not the sides. So DB is considered a diagonal, AC is considered a diagonal. We want to show that those diagonals are the same length. AC and BD are the same length. Well, for us to do that, it might help to draw the shapes separately so they're not overlapping. You first need to know what triangles you're working with. You need to pick the triangles that have the entire diagonal from A to C, back to D, and from B to D, back to C. Those are the triangles we're working with. We know that AD is supposed to be congruent to BC. AD is perpendicular to DC. And BC is perpendicular to DC. That's what we know for sure. Now, if you look back at the original shape, is there anything else that we could be able to tell about our triangles? We're looking at two different triangles. We have this big triangle. We also have this big triangle. We've been using some highlighters in class to help us identify what shapes we're working with. Notice that some of you might say that vertical angles are happening, but remember, for the orange angle here, triangle, we don't have a vertex at E. So no, vertical angles are not part of this. But the side that's the same as this DC. we have a reflexive side called DC. Now if we look at this side angle side, then we can say the corresponding parts are congruent. I made the plan before I did the proof. You've got to look over the picture. You've got to use your given information to determine that first. AD is congruent to BC. AD is perpendicular to DC. We also know that BC is perpendicular to DC. That was all the given. I decided to write it all up front. Now what does this perpendicular stuff tell us? What do we know? What do we always say when you have two segments that are perpendicular to one another? We have right angles. So angle ADC, comma, angle BCD are right angles. If perpendicular, which we have, that was the given, that happened earlier, if happens earlier, then right angles. Now, we have some choices. We could either talk about how this makes right triangles, and then we might be able to use RHL, or we could make the right angles congruent to each other. RHL would require us to know that the hypotenuses were the same. We don't know that. In fact, that's what we're trying to show, so we don't know that right now. So we're not going to do right triangles. We're going to say that angle ADC is congruent to angle BCD. Those are your right angles. Right angles are congruent. If right angles, that's what we talked about earlier. We stated the if part earlier. Then congruent angles. Because right angles are always congruent to each other. We also have, what's the next part we haven't discussed in the proof? We discussed it in the plan, but we didn't discuss it in the proof. DC is congruent to CD. DC goes from the right angle out to the point, and CD goes from the right angle out to the point. Reflexive POC. What's my fifth step? What are we ready to do? What have we accomplished? We have talked about a side, we've talked about an angle, and then we talked about another side. So triangle ADC is congruent to triangle BCD. And that was because of side, angle, side congruence. And what's my last statement? It's always what you're trying to prove. And for what reason? How do I know those two segments? How do I know AC is congruent to BD? Once I show the triangles congruent, the first and last letter are going to match the first and last letter. Those are called corresponding parts. If two triangles are congruent, then corresponding parts are congruent. So we first talked about the perpendicular, which made right angles, and right angles are congruent. We had the reflexive, so now we're ready to talk about the congruent triangles, and then the corresponding parts are congruent. Here we're going to prove that the opposite sides of a parallelogram are congruent. These are all the lessons we're doing in the future. Chapter 5. So we're going to prove that the opposite sides are congruent. We're going to look at AB, segment AB is parallel. So what are we supposed to think about when we hear parallel? Zigzag. We're looking for the zigzag. There's a zigzag. That zigzag shows us exactly where those angles we're going to talk about. Those are alternate interior angles. We have another pair, and they're going to go up, down, and through, which are going to give us these two angles. And then we have the reflexive side. So the triangles are congruent by side, angle, side. And then once we get to triangles congruent, then the corresponding parts are congruent. So let's see, taking that plan, let's see if we can write this out. Number 1, AB is parallel to CD. We also know that AD is parallel to CB. That's the given. Okay, once we have parallel lines, what are we supposed to talk about next? We always talk about angles. So let's name our angles we had here as alternate interior. ABD, the B is your vertex, so that's this angle in here. And it's supposed to be congruent to CDB. Angle CDB. I also know that angle ADB is congruent to, that made the 2-ticker line, so CBD. Both of these, if parallel lines, that's what we have, then alternate interior angles are congruent. You have to name the angle. Don't just say angles, don't just say congruent, you have to say alternate interior angles. Okay, what's our next step? We've talked about some angles. We have to get a side in here. We'll go from the 1 tick mark to the 2 tick mark, DB. That's actually BD. And that's from the 1 tick mark to the 2 tick mark, DB. That's called the reflexive POC, property of congruence. What do we do next? We've talked about angles. We've talked about a side. In our picture, that gave us 2 angles and the side that connects them. So now we're ready to show that triangle ABD is congruent to triangle. Got to be careful how you write the second one. A was the one on the outside, so we got to start with C. B had the 1 tick mark, so I got to use D as my 1 tick mark. And then we ended at the 2 tick mark, so we have to end at the 2. So order matters how you label that. And that was because which of the 5 ways are we going to use? Angle, side, angle. We have 2 A's and the S in between. And then we can finish up with what we're trying to prove. We're trying to prove that segment AB is congruent to segment CD. And we know that AD is congruent to CB. That's what we're trying to prove here. Those are the sides of our polygon, AB and CD. AD and CB. The opposite sides are congruent in this parallelogram. A parallelogram has opposite sides parallel. That's what we're trying to prove. Opposite sides are congruent. So if 2 triangles are congruent, then corresponding, if you want to say corresponding segments, that would be fine because these are segments, but corresponding parts are congruent.